So with that, I'm pleased to turn it over to three of my colleagues at Google, Bill Magro, Felix Sherman, and Annie Ma Weaver, who are going to give you a comprehensive overview of Google Cloud's capabilities for HPC AI, data analytics, and more. So let's bring them all on screen. Thanks for joining, guys.
Hey, everyone. So hi, I'm Bill Magro. I was with you in our last session, and I want to just continue a little bit and go a tiny bit deeper than we did last time. So last time we talked about the fact that cloud computing is growing in adoption within the high performance and advanced computing community. And I think one of the things we emphasized was that cloud computing is really not always the best way to solve every problem, but it can be the best way to solve some problems. At the same time, on-premise systems are the best way to solve other problems, which is why we really want to look at this world of hybrid and see where the best things fit. So it's interesting to look in just the last 6 weeks, some of the things that have advanced or progressed in the world of advanced computing. And so in the on-prem world, El Capitan, right, #1 system in the world, exceeding 1.7 exaflops, very impressive. Other things, Nobel Prize in Chemistry, a couple of Google employees were part of that for their work on AlphaFold, which is predicting the structures and interactions of all of life's molecules with unprecedented accuracy. Really surprising and exciting was to see the Seymour Cray Prize go to Norm Juppy, also a Google employee, for creating innovative AI infrastructure with the tensor processing unit. So we're going to try and get Norm to come talk to us early in Q2 as well about the TPUs, where they've come from, where they're going, and not just AI, how they're being used for direct simulation and scientific computing, and also for AI for science. And then, as Jay mentioned, Willow, the state-of-the-art quantum chip, another Google innovation, very exciting to achieve below threshold error correction, which has been something the community's been working towards for years and years, which really means as you scale chips up, the amount of noise goes down. And one of, I think, the most impressive things was with this 105 qubit chip, we were able to do in about 5 minutes a calculation that is estimated to would have taken 10 to the 25th years on the fastest supercomputer in the world, i.e. a system like El Capitan. So it's quite exciting to see the prospects for quantum in the coming years. So as Jay said, we're going to be talking about all kinds of advanced computing technologies here as we go forward. So returning to a slide I used last time, the point we were making is that cloud is becoming an option for some of the hardest problems, not necessarily all of them, that, far up in the right capability systems, just like El Capitan. We're not trying to compete with that, but as cloud gets more and more capable, you have more choice about where you run your workloads. And that's going to be an important part of what you hear about today. So in terms of advanced computing on Google Cloud, we really think in terms of two things. A lot of our customers and the most exciting and interesting things they're doing, and our partners, are often the right, where they're using some of the most advanced capabilities like extreme scale Kubernetes, extreme scale data analytics, increasingly AI for science and quantum computing. But many of our customers and really find cloud most approachable when they can see how to do things that are already familiar to them. So solving the same kinds of problems that they solve on premise, but maybe doing it with different infrastructure or a different scale. And so we've kind of built our high performance computing program around focusing on meeting people where they are. And that's what we're going to really talk about most today. So one of the first principles is what we call easy and compatible. And that's about creating familiar software environments where you can bring existing software, existing workflows, existing workloads, and with no changes, run them. And what that requires is an HPC-aware control plane, meaning cloud in many ways was not built for HPC. So we've had to update our cloud so it is aware of HPC and natively can provision those types of environments. And then, of course, the tooling to create those turnkey environments so that you don't have to learn cloud APIs, which can be incredibly broad and incredibly daunting. And for busy researchers and HPC professionals, we just want to get our work done, right? In terms of fast and affordable, it doesn't really matter if you can provision a compatible environment if it doesn't perform, if it's not affordable. And so we're constantly needing to bring in the latest in technologies and tune them and deploy them with specific feature sets to enable scalable HPC workloads. And you're going to hear more about that today. And then a broad choice of consumption models. In on-premise, it's generally you have to pick a relatively homogeneous system. You own it for a number of years. And there is no particular consumption model. You're paying for it, whether through a lease or direct purchase or a service agreement. but then you just consume through a queue. But in cloud, we actually have a number of degrees of freedom in how we offer things up, and so you're going to hear something about that today. And then finally, we realized that we don't kind of control all of the software. We don't answer all the questions. So working with our partners to bring in the compatible applications, the software systems, even turnkey solutions, and working with integrators is a key part of our strategy. So during today's session, we're gonna talk about those things. But I want to double click real briefly into this notion of a control plane that's HPC aware, because a lot of people, I think, are aware that cloud was not built for high performance computing, which means that going off and getting things like and just asking for a cluster on demand, you maybe wouldn't get it, or you get a collection of resources, but not all of them are available at the same time. Or maybe they are available, but they're so far apart that you have poor performance. So one thing that we've been doing, and we're putting it under this label hypercomputer, is really doing an overhaul of the way we provision high performance computing systems in Google Cloud. And so we're going to hear about this in detail from Felix in just a moment. But some of the key features are doing what we call dense deployments, which means building physical supercomputers behind the APIs, and then creating the APIs so that you can provision against those and discover the topology, which lets you get better performance and better scalability. In order to do this, we're having to leverage Google's innovative scheduling algorithms, but I think folks are aware that we run, I guess we don't disclose the specific number of systems, but lots of systems around the world. And so there's a very sophisticated scheduler out there, and we've integrated that up so that it understands HPC clusters as a first-class citizen. And that in turn is enabling us to do innovative consumption models where you can actually ask for clusters for a short period of time, whether it be for a campaign or a job, and you're going to hear more about that from Annie. And then another thing about cloud is it really is built around this, this cattle versus pets concept, where it's okay to maybe have a machine disappear because the workloads are resilient. And that's not always the case in high performance computing. And so what we've done is a lot of enhancements, and we give you controls over maintenance, and just like we would have on premise when you decide when to take systems offline or online, and also built-in resiliency where we manage spares, and particularly in the world where we've got some accelerators that tend to be not as reliable as traditional CPUs, being able to say, I don't necessarily trust this machine, send it away and give me a different machine in its place. We're putting those types of controls in place so that you can get built-in resiliency and more control like you will with an on-premise system. So just to summarize what we're doing here today, we want to give you a broad overview of the capabilities we're putting in place for high performance and advanced computing on Google Cloud. And this is really not so much to advertise with Google Cloud, but rather to give you a frame of reference, because in future sessions, we will be diving deeper in a lot of these topics, both from us and from our partners. So today's focus is really going to be about the supercomputing capabilities, which Felix is going to take us through. And then Annie will talk to us about some of our partnerships and consumption models. And then, as you heard, in the future, we're going to hit a bunch of other more advanced topics. So with that, I'll hand it over to Felix.
Thank you, Bill. Hi, everybody. It's great to be here. I had a life before Google. I started my professional career in a large-scale mission-driven science project and was providing and using and overseeing the use of on-prem supercomputers, multiple generations in the last 20 years. And through that 20 years, I actually realized that sort of our the science mission and the users needed more and more services in addition to the high performance computing. So they actually asked for object stores. They asked for web access to the high performance computing. They wanted Jupyter notebooks, having access to the high performance storage. They wanted 24/7 access because we were collaborating in a big e-infrastructure project. So we actually had to build all these additional services in addition to our high-performance computing system. I was very happy when Satoshi Matsuoka and colleagues actually found a name for what I've been witnessing. They called it the cloudification of supercomputers. And I think we can discuss about the semantics, but I think it's describing exactly this, that sort of we are seeing that our science and engineering workflows need more than just the number crunching part. Now, this progression, of course, was happening on the cloud side as well. So since I joined Google, I, on the one hand, saw that a lot happened in cloud already in these last 10, 15 years, and more is happening now. And there are multiple factors to that. One is, of course, part of it is done by how Moore's law put more transistors and more functions into individual processes. So each node was able to run larger workloads. But in cloud, we've seen now that our users and customers have been bringing more workloads to cloud, which are requiring tightly coupled shared fate and large scale computation. So Satoshi and colleagues gave also a term for that, and it is they found it the supercomputification of cloud. And I think that describes quite well sort of how from two sides we're becoming more similar and now can consider solving the problems in different ways. To give an example of a piece of equipment that is in our data centers multiple times, and Bill alluded to it. So this is a TPU V5P chip or SuperPod of an accelerated chip developed by Google. And Google has been developing these TPU chips since 2013, and they are deployed in this way. So these are close to 9,000 chips, water-cooled, sitting side by side in racks which are crammed close to each other. And this has multiple reasons, of course. It is really about minimizing the network's latency when these chips collaborate for one problem. And it is limited by the physics, right? Speed of light does matter, and the closer your wires are, the faster the signals travel. And also, of course, minimizing the network hops so that you can reach, every node can reach every other node, or your collective operations can succeed very quickly. So these dense deployments isn't necessarily what cloud would have started out with when it comes to e-commerce functionality that needs to be redundant and resilient to Black Friday shopping frenzies around the world. And you want to actually place these resources in multiple zones and multiple regions around the world. So I'm looking at this, it's sort of how, in a way, HPC concepts come into cloud and cloud concepts help HPC. So dense deployments is something that I think HPC brought to cloud for the types of workloads we've seen in HPC before. Now, in cloud, we're running with this abstraction, right? We use virtual machines on top of the actual bare metal hardware. So it isn't sufficient that we are putting the hardware close to each other and densely packed. We also need to make sure that our scheduling mechanisms that provision the VMs on top of this hardware are aware of that. On the left-hand side, you see a mechanism which sort of is good when we are trying to make applications resilient. So we spread them out, don't put them in the same rack or in the same zone. In case of a power outage, you actually can recover from losing certain parts of your infrastructure. In HPC, we're willing to take that risk because of the said reasons why we want to have our resources densely packed and then placed onto this densely deployed hardware. So this is a concept that cloud we have to teach cloud. And you can choose. So because obviously the left side mechanism is still useful for certain business critical applications, and the right hand side you might choose if you want to maximize the performance. Now that we established sort of how we actually have to deploy resources in the cloud, you do need to have the right resources or the right node types to actually deploy. And the image you saw earlier, so this are the blue boxes down here. The TPU accelerators, which we've been using in Google for training machine learning algorithms since a long time, they've been obviously custom-made chips. They don't have 64-bit precision double floating point. They are made for AI inference and training. We've equally, with of course the last 2 years and the generative AI frenzy going on, we've been deploying node types that host NVIDIA GPUs, especially the NVIDIA H100s and the NVIDIA H200s. So these are in Google nomenclature, these are our A3 accelerator VMs of the 3rd generation, supporting 8-way GPU configurations with these GPUs. And we have NVIDIA B200 and GB200 upcoming in the new year. And then for more traditional technical and scientific computing workloads, CFD simulations, risk calculations, weather modeling, we have CPU VMs, which I list here in yellow. For example, last year we deployed our first HPC-specific VM machine with Intel Sapphire Rapids chip. We have the AMD Genoa with the C4D, and we have, of course, prior generations, which are still interesting because of their high frequency and well-balanced memory bandwidth to clock frequency configuration. And we're very excited. We are rolling out our next iteration of the high-performance VM family, which will be based on AMD Turin, and I'll speak about that in a little bit. So this is obviously just a subset of the VMs you can find in cloud. We have the Axion ARM variants for cost-effective performance. We have machines which are very large memory footprints. So you will find all these types of machines that cater to different types of users and users. But I think here I'm showing you a selection of machine types which our customers use regularly for high performance computing. And you can mix and match them depending on what are your requirements. Now, densely deployed, the right types of nodes, you do have to now wire them up together. And as you can imagine, in Google Cloud's data centers, we have been at this problem since a long time, serving Google services, but also serving our customers' workloads. And in a way, we call that the Jupyter network. This data center network is in fifth generation. And we've been building these close architectures where you have the machines, the top of rack switch, aggregation blocks, and then through the spine layer, you can essentially have an all-to-all connectivity between your workloads and the outgoing endpoints of the internet. Now, the downside of this architecture is that if you are rolling in new technology, for example, now a faster, higher bandwidth network device, for example, going from 100 gigabit to 200 gigabits, then you actually have to, in the spine layer, deploy these faster spine switches, but they're not being fully utilized for the 200 gigabit links because you have to all connect them to the other aggregation blocks. And so the challenge we have in cloud is to keep our network technology, network equipment ready to absorb these newer generations without having to replace or rewire our data center network. And this problem has been quite prominent in Google Cloud, and a solution was found, and we developed these optical circuit switching mechanisms, which are MEMS devices, which are literally little mirrors, which allow us to reconfigure our network. So we essentially replace the spine layer and sort of bring the optical circuit switching in, which allows us to form arbitrary topologies between aggregation blocks. And we just published a blog where we showed that this data center fabric can get an aggregate bisection bandwidth of 13 petabits per second between all the connected endpoints, if you wish. And so this is something which we in Google, we don't roll out separate new systems as we often do in HPC centers, but we actually have to keep our machine environment able to absorb new machines as we're rolling them in and rolling some others out. Now, on that backdrop, we have a data center network which is high performance, and it can be shaped for applications. And the complement of that is you have to have in your hosts and your VMs the appropriate NIC hardware that allows you to use this data center network. And so we've been developing over the last couple of years what we call the Titanium Infrastructure Processing Unit, which is a NIC, a smart NIC, which allows you to do all sorts of offloads, meaning you have hardware accelerated support for different types of protocols. So we can hardware accelerate NVMe protocol, we can hardware accelerate RDMA, we can hardware accelerate other protocols. We have inline encryption on this IPU, and we can shape traffic, and it can use the data center network that we have. From a user perspective, for example, to allow RDMA, we have to enable RDMA over Ethernet because our data center network is Ethernet. And in order to support the different things we need to do, quality of service, traffic shaping, Google developed a new transport layer, the Falcon layer, we call it, and it has been given to the Open Compute project as an open source. So this is an implementation that allows us to do all the things we need to do in the data center, yet support RDMA, so remote direct memory access between VMs. We are providing the appropriate drivers and show this capability to the user space as libfabric and libID verbs providers, which means that from a user perspective, you can use these capabilities of RDMA without having to change your application. So if you're using MPI, and MPI is configured to work against the libfabric provider, you literally can make use of this new capability right away. So this is for us quite an exciting time. So we are for the first time switching on RDMA in the host-to-host communication going forward in the new year for this new generation of high-performance computing VMs I've been alluding to based on AMD Turin. And that is allowing, so without any further change, because essentially we've decided in Google not to put separate systems that do HPC and have HPC wiring into our data centers, but we made RDMA work on top of our data center fabric. Now we have the compute and the networking infrastructure, and to have complete HPC systems or AI infra systems, you do need to also have high performance storage. And of course, there are different types of storages. You might want to have block storage local to your nodes, and you have different choices in Google Cloud. I will not go through all the different variants, but I want to point out that you, of course, can have local SSDs with an NVMe interface in your GPU or CPU VM shapes. But the offloading technology we were just talking about allows you to also offload NVMe protocol. So we have now with Hyperdisk have the ability to present a block storage device to VMs without having to provision it locally in the hosts. And we can disaggregate the bandwidth requirement from the IOPS, allowing you to choose if you need a certain type of local block storage, which is only throughput for a throughput-oriented application. You can just dial in the appropriate size and throughput. If for another VM you don't need anything, you don't need to provision this hardware in the nodes, or if you need a high IOPS variant, you can dial that into. This is accelerated through this intelligent processing unit, the IPU, which we've been rolling out in our third generation VMs. Now, this allows us to do other things. We actually can now, a problem statement, which is we're seeing often now in large AI infrastructure and AI training jobs, is how to deliver the container images to all these thousands of nodes. So this offloaded block device can be configured in a way that it can provision a read-only environment to thousands of VMs, producing an aggregate of in the order of terabyte per second read to deliver, for example, an immutable image to the different nodes. That's block storage. We have, of course, those file storage, which in HPC world typically means parallel file system. So we launched this year Parallel Store, which is a parallel file system based on Intel Deos, which is very well suited for large bandwidth, high IOPS at reasonable capacity. So many times in parallel file systems, you have to crank up the bandwidth, the capacity in order to reach a certain bandwidth. And Deos, which is different in a way, it's done by the Lustre developers as a new generation file system, allows you to reach high bandwidth and high IOPS at already low capacity. Now, in HPC, of course, we do trust file systems that have kept us safe and powered our systems for the last decades, like IBM Spectrum Scale and Cluster. So in this model of being open to partners, as Bill had mentioned earlier, we do offer that you can run Spectrum Scale or Cluster through partners in Google Cloud. And there you decide how many storage nodes you bring and how many metadata servers you bring. So you can actually dial your bandwidth and IOPS accordingly. And I want to say, it doesn't look like an HPC file system. Our Google Cloud Storage, which is an object store with relatively high latency, but it does do quite some magic. It's a global file system with many properties that are interesting, and it can scale from 0 to terabytes per second if you have enough readers in that. Now, if you can hide that latency, this is an extremely high performant and at the same time very cost-effective storage. And we have customers that started that when they came to cloud from an on-prem configuration, said, oh, we need a parallel file system of a large size. But they realized that they can hide the latency and use the cloud storage type. So these are types of journeys that everyone can start when they are coming to cloud. Now, one thing that we do in on-prem is, of course, we spend quite some time configuring our next system, thinking about what are the specifications, and then order that system, will roll in the hardware, deploy that system, and operate that system for multiple use. And then probably some systems are operated for 4, 5, 6 years. And depending on the site, you have these longer cadence procurement and deployment schedules, or you might actually upgrade your system every other year in order to accommodate for demand. Now in cloud, there is some analog, if you wish. Now we are deploying the hardware as Google. You're not buying our hardware; you're renting our hardware. So this renting is, you can to some degree see as almost the same thing as when you're deploying and installing your system. We need to do that within minutes, so that when you say, I need that hardware, that we can give it to you. So what I'm trying to illustrate here is that the same thing as in on-prem, you do a configuration of compute, network, and storage, and you might run this for a long time. You might start to elastically grow and then launch additional instances of that service, and then you bring them down. And what you now sort of talking about, that sort of you could have this more loosely coupled type of resources, but you can now also bring up densely coupled environments up in cloud. And of course, in order to do that, everything has to be software defined, because there can't be any manual interactions when you have this infrastructure react and swiftly to your requirements, and if you want to have a repeatable and reliable high performance environment. So in order to do that, we built the Cluster Toolkit, which was previously known as the HPC Toolkit, because it came from those in Google Cloud being aware of the problematics of how between all the cloud possibilities do you choose the ones that are trusted and proven to give you high performance. And what that means is, so this Cluster Toolkit is actually opinionated. So it has a certain number of modules for, let's take example, the different high performance files options, storage options we have. So anything from cloud storage, file store, DDN and exascale, Cluster. It has knowledge about compute instances, whether it's CPUs, GPUs, or TPUs, the ones, for example, suited for HPC. It has notions of other cloud concepts from virtual private clouds, firewalls. It's connected to monitoring, logging, and it has different schedulers and runtime environments. So, for example, you can bring up Slurm on the virtual machine backend, our Google Compute Engine, or you can bring up a container platform like Google Kubernetes Engine. And it is not to say that you want necessarily all of that. As a matter of fact, the animation that was running here is showing the fact that depending on the customer, you might choose different parts of Google Cloud. For if you're doing AI infrastructure, you might decide to use these A3 nodes with NVIDIA H200s. If you are somebody who is designing the next generation airplane and you're running CFD, you might be using a CPU-based partition with Slurm. And this is what I think is what excites me most about this the discussions we're having here, that I think we're really seeing how we can now adapt the infrastructure to the actual problem that needs to be solved. So here are just 3 examples of repeatable turnkey high performance environments, which are for HPC or AI infra, or maybe you don't neither call it HPC or AI infra, but you can think of bringing up in cloud an auto-scaling HPC cluster, which has login nodes, controllers, which has partitions. These partitions might have a reservation of nodes which are always on. These might have nodes that are auto-scaling as sort of Slurm gets aware of more jobs in its queue. It does the resource management side of it and brings in new resources from the Google control plane. You might have partitions that have GPUs, and maybe you need them always on, and you keep a static reservation of the partition. And the users log in like you would in an on-prem system onto a login node with some Linux variant and submit jobs to the Slurm queue. And you might here, again, very similar to on-prem, provision certain types of file systems that are of certain qualities, for example, a GPFS spectrum scale or Lustre system, and that sort of has certain types of partitions as you are aware of from on-prem systems. And this is where these the hypercluster controls come in, that you can go as far as now doing, for example, the maintenance controls for these nodes within that partition. So you can decide when to do that maintenance. You can obtain these resources through scheduling mechanisms in Google Cloud. So we've been, by promoting this notion of system construct, you can really build a high performance cluster, or an AI infra cluster that very much behaves similar to a system that you would have on-prem. But you can also do other things. So instead of saying, well, we are not a shop which knows how to install an HPC schedule like Slurm or PBS Pro, but you are coming with containerized workloads, and you actually do AI training and inference. So you want to choose or share your resources that you have, the precious GPUs you have, between training, and then once you're not training, you want to use it for inference. So we have many customers that come to Google Cloud using Google Kubernetes engine for that, where you then have node pools that are auto-scaling of certain types of nodes that can be, again, CPU nodes, GPU nodes, it can be spot instances, and the GKE control plane orchestrates these resources for you, including access to the appropriate storage systems, for example, like the container distribution we've been talking about. So independent of whether you run this on GC, so against virtual machines, GKE with container backends, you will get the same high performance tunings and controls that we've been talking about. So the network acceleration, the OS image optimizations, all these elements that sort of make your application run high performance is available here. And to give an idea for customer sizes, we have customers that run thousands of nodes, meaning for 8-way GPU VMs, this can reach tens of thousands of GPUs or TPUs, or millions of cores in the CPU land. But the interesting thing is you can think of both of those systems in a way as infrastructure as code, but we can also do environments as code. nothing prevents you from tailoring the resources to an individual application. You wouldn't do that on-prem, right? Because you have shared resources, and you design your file system and your compute types so that you can serve a range of customers. In cloud, you can actually say, well, the optimal set of resources for running, for example, my genomics batch application is you can hide the latency. I can read directly from cloud. They're loosely coupled from cloud storage. The individual worker nodes are loosely coupled, and they can write back to cloud. So you're not paying for a parallel file system. You're not paying for low latency. You literally get the optimal set of resources to run your application. And you can mix and match all of that as it's software defined. You can decide to give resources to an environment that exposes them to Slurm. You can give resources to an environment that exposes them as a GKE cluster or individual applications. And so for me, what this really, it opened the perspective that if you have these mechanisms of cloud where you no longer have a capital expenditure of your hardware, you can do something which I think is one of the most exciting parts in HPC. Namely, you can really think about what requirements does a computational problem has, and how does that optimally fit and match to hardware. And with that, Annie, I'll give the word to you.
Great, thanks, Felix. Appreciate you giving us that overview, and then I would like to tell you more about consumption models. So for those of you who don't know me, I'm Annie Ma-Weaver. I'm a product manager on Bill's team, and I've been fortunate to work on Cloud HPC for 8 years and getting to see the rapid evolution of it during that time. So one of the ways in which we are thinking about bringing, to Felix's point, more of HPC to cloud is how we can use these HPC concepts of cluster management when we're thinking about resource allocation. So our consumption models run the gamut, or like span from more on-prem like with our committed use discounts and our sustained use discounts, or CUDs and SUDs, to more cloud native, which we call on-demand or OD. And then somewhere in between there, we have spot VMs, which are flexible. They can be preempted, but there is a graceful termination of a 30-second notification before preemption. And so it is well suited for disruption tolerant workloads that are stateless and can restart any VMs that are spun down or preempted. With spot VMs, you can see a minimum of 60% up to 91% discount. So it can often mimic or even match what it costs per core hour on-prem to run on-prem versus in cloud. And we know with HPC that cost is a very important factor to keep in mind as we spin up these large amounts of compute resources. Something that we are developing right now and is becoming available with more and more of our compute resources is the Dynamic Workload Scheduler, or DWS. And so DWS is our way of giving access to compute resources, especially limited access, high demand resources. So you can think of GPUs and in the future TPUs, and also our H series HPC VMs, which Felix talked about. DWS allows customers to queue multiple resource requests with time-bounded quality. So you can schedule which machines you need for the future. And there's two main modes, flex mode and calendar mode, where you can tell us like what period of time you can flex in or what specific time you want it with calendar dates. It elevates clusters to become first-class citizens to serve a specific job or campaign. And the benefit is actually mutual, or like two-way, in that it gives us, Google, more information to run our fleet more efficiently, which over time will allow us to deliver better economics across our fleet, across customers using these resources, so we can make HPC more affordable for cloud customers. So this is something that we are, as a shared making available for our next HPC VMs. Our H4D, the AMD Turin-based offering, is going to be in private preview starting in January, and that will be DWS enabled. And then we also have the H4s, which are Intel processor based, and those will also be DWS enabled. So you're going to be hearing a lot about DWS from us, and definitely watch this space. And when you see it, this is something that we think is very HPC friendly, HPC congruent, and we're glad that we can build up this concept internally and then launch it to this community. I want to talk about partners. At the very beginning, when Bill gave the intro, partners really are important for us because with them, we can build a complete solution that really complement and complete our native offerings. And we work with a broad ecosystem, a plethora of partners, as you can see, because HPC requires a lot of integration points, a lot of application support and infrastructure support just to get that cluster running up to the high performance requirements that you have. So I want to highlight some of the partners that we've worked with over the years and talk a little bit about the solutions that they have. So the first partner I'm going to talk about is Parallelworks. We worked with them, and they did with GDIT to enable the NOAA RDHPC HPCS contract, there we go, with their Activate platform. And this allowed NOAA to achieve supercomputing performance levels on their hybrid setup for their key weather application codes. And so one of the things that NOAA was concerned about was securing access to their on-prem supercomputers and then scaling elastically into the cloud with multi-cloud capability. They actually ran a POC on multiple clouds, and only Google Cloud working with Parallelworks was able to meet their performance requirements. And so the Activate platform is validated for those very high security, high regulation customers such as NOAA, and we're very excited because we see that space as one that's gradually and then maybe more quickly moving over to cloud and working with a partner like Parallelworks to enable that move. SCEDMD, for those of you who have heard me speak before, I'm a huge proponent of what we're doing there with Slurm GCP. Slurm GCP is a software-to-software interface layer, reducing the complexities of deploying and running Slurm on Google Cloud. It makes the life of our Slurm admins much easier, and that's something that we think about a lot working in HPC. We also want to make a lot of the Slurm configuration features that you can enable with Google Cloud more transparent to both users and admins. So we developed this jointly with SCEDMD back in 2017, launched it in 2018, and then as of this year, we actually transferred ownership of the engineering work to the Google Cluster Toolkit team. And V6 just went GA earlier this year. Some of the main benefits there are faster deployments. A simple Slurm cluster now deploys 3 times faster than with V5. 2 more partners. So DDN, they have a offering called Exascaler in a marketplace. It's enterprise-grade Lustre parallel file system with full support, and it's exclusive to Google Cloud. That support includes professional services and white glove capabilities to help migrate and fine-tune your Lustre implementation. And then last but not least, NVIDIA. We've been working with them to co-ensure performance of their GPU generations. And we've created workload-specific solutions like our NeMo blueprint, which I developed with the NVIDIA PM for NeMo and the Cluster Toolkit team. And then we have optimized for each subsequent A-series offering. So with that, I'm going to hand it over to Bill to let you know about more advanced computing technologies.
Thanks, Annie. Given we've only got about 10 minutes left, I'll just let folks scan some of the things we didn't cover today, but these are things that would fall into that third column, along with some of the things we're going to hear about from our partners and other customers. And with that, I'll hand it back to Jay.
All right. Thank you, Bill, Annie, and Felix. I'm going to ask all of you to come online here, and we're going to try to get through a few questions before I cover my final slides so we can inform our audience about the things we've got coming up in January and beyond. We're only going to be able to pick a few questions, but we'll save all the questions and answer all of them offline in early January. And coming in early January, you'll be able to ask questions live during this session. And then we'll be able to address remaining questions asynchronously as we integrate more Google tools like Google Chat into this community. So a couple of quick questions. I'll answer the first one. Sharon Kawani asks, is the previous and current session recorded and available for viewing? Yes, it is. Mary or Wyatt has pinned that message into the chat for you. We have a Google YouTube channel for these talks, so we're going to make sure that they can be seen offline as well. Another question, Adnan Khalil asks, is Titanium based on the E2000 IPU, which was a joint collaborative effort between Google and Intel?
Yeah, I can take that. And then, so the Titanium is a broader set of technologies for offloads and advanced networking and virtualization, but the specific IPU that we were describing today is in fact the collaborative one with Intel that goes under that product name. And relatively easy. If you do a quick search, you'll see that same image that we showed today.
And another question that might be a quick one for you, Bill, from devs@dritzy.com. Will the LibFabric provider for RDMA be included in the base Rocky images?
Yeah, we work closely with Control IQ on Rocky Linux images, and then our HPC team builds on top of that HPC images that integrate key pieces of software like the drivers for the RDMA, LibFabric, libIBverbs, systems like SPAC, tunings for Intel MPI, performance profiles, and so on. So yes, you can expect to see turnkey systems at the node level and then turnkey blueprints for full clusters that incorporate everything you'll need for RDMA.
Great. And another question that might be pretty quick. Daniel Zivkovich asks, are there any plans for Cloud Run, not just GKE support?
Unless Felix or anyone want to take that, I could take it. Yeah, I'd be happy to. So Cloud Run, for those not familiar with it, is a serverless solution where you can provide your containers and your workloads. And absolutely, there's a very, very wide range of services available through cloud computing. And if that fits for your workload, that's something you certainly can use. Today, we tried to focus more on what are the things that we need to do that are unique to high performance computing to enable scalability and performance. But we've been, and you're going to hear about this in a future session, for almost 4 years now, we've been putting a lot of advanced capabilities into our Kubernetes service, GKE, and into the way we handle containers in terms of staging them and caching them so that it becomes much more capable for high performance computing workloads. So while we haven't shown you today anything specific with Cloud Run, that could be a good deployment vehicle for you, especially for automating workflows into, say, scripted environments.
All right, thanks, Bill. Chris Cowan asking you please post the Google channel name. I assume he means the YouTube channel, and that has now been posted again in Slack. Another question that we can answer real quickly. Kanhaya Sharma asks, what are some of the disruptive HPC use cases for 2025? That actually is a short question with a very long answer, but fortunately it's the topic of our next session on January 7th. So I hope you'll tune in on January 7th. We're going to have some global leaders in HPC address that very question. And we'll take one more here before we give the final announcements. Let's see. I'm going to ask a question from Bill Turner. I'm not quite sure what Bill means, but maybe Felix, Bill, or Annie, you'll get this. Am I clear in understanding that for every GPU cycle, I could configure multiple VMs running multiple clusters to attack a Navier-Stokes type equation? Why don't, that's a little bit confusing, I think, as a question, but why don't you address what it means in these, to have these multiple GPU VMs for doing Navier-Stokes type problems?
I can try to take a go at this question. I think there is, at the end of the day, an application running is using the underlying hardware. And sort of if you're running an application on one GPU, which is fully utilizing that, in this case, let's assume it's a CFD application, then you would need additional GPUs and additional instances of that software to run additional multiple clusters, which you can do, right? And on-prem, you might have, I don't know, 1, 10, 100 GPUs, and in cloud, you can rent additional units if, for example, you want to get to a faster time to solution, or you want to run more ensemble type simulation. So cloud allows you, of course, to farm out your job on more resources than what you possibly might have on-prem. Now, there are more advanced things, like GKE can share GPUs between applications if it happens that certain applications are not using the GPU all the duty cycles. So there's some additional harvesting that you can do in those situations. I think I'll stop here. I mean, just trying to say, I mean, at the end of the day, in cloud also, we are running on real hardware. So there's no magic multiplication of the underlying hardware. But you can think of sharing, and you can, of course, elastically scale.